Hi everyone, welcome back. We're going to talk today about multiple regression, having already talked about simple regression last week. And in reality, we don't really use simple regression that often. There's really not very many advantages over other bivariate techniques. But we often start with a simple regression and build towards multiple regression, especially in order to obtain a crude estimate of the effect of one variable on outcome, and then looking to see what happens when we add additional variables to that model. So I don't want to ignore the importance of simple regression, but it's part of the steps that we would take moving towards more advanced methods or more inclusive methods that allow for multiple variables, including adjustment for confounders. So multiple regression, we say, is conditional. That means that our parameter estimates that we obtain from the model are conditioned on other variables in the model. It's kind of a fancy way of saying that there's an association among the independent variables that we need to take into account. And so what we're parsing out are the independent effects of those variables after you've taken into account the other variables in the model. And that's what we mean by adjustment. So once we've conditioned it on the presence of age or conditioned it on differences in sex or whatever it is that we're measuring, that parameter estimate is taking into account those other variables, which is very different than what we've done so far, which is purely bivariate analysis, where we're saying this is the effect of this variable on outcome. We can somewhat assess the relative importance of our different independent variables by the p-values. However, I don't recommend that strategy because ultimately a p-value can depend on a lot of things, including the counts in each group, and it could have to do with the strength of a relationship in terms of our sample size. And so I wouldn't rely too heavily on p-values, but it is one way to kind of gauge what is more important than what in our model. In linear regression models, we can request that we produce standardized beta coefficients. Rather than expressing in the original units, it expresses it in terms of z-scores or standardized versions of those variables. We don't generally do that in medicine and public health. I think the reason we don't is because we are actually interested in the original units. That helps make clinical decisions and clinical significance more easy to read. However, if you did want to kind of get a weighted sense of how much each variable is contributing, that would be one way. We can also do formal statistical tests to determine which variables are most important. However, we usually are more interested in their clinical relevance or their epidemiological relevance once we've established that there is an association. So multiple regression is super useful for statistical adjustment of confounders, and we can also explore and test effect modification. Doing so requires us including interaction terms, which I'm not going to get into in this course, but by including an interaction term, we can model effect modification. However, it can be very tricky to interpret models that include effect modifiers. And so we often want to start with a stratified analysis to kind of get our heads around what is happening as far as effect modification, and then moving to a model and interpreting from there. So in multiple regression, the independent variables or predictors can be continuous. They can be indicator variables, 0, 1, or yes, no, or a set of dummy variables that represent membership in different categories. And what this allows is really any level of measurement. We can have ordinal measures that we treat as dummy variables. If we decided that the distance between those categories was pretty similar, we could actually then re-enter it as if it were interval, continuous and interval variables, and then of course, any number of dummy variables. So it really is very, very flexible, and that's one reason why it's a very popular method. The downside is that a reliance on regression techniques can lead to some bias, especially because we are assuming that these variables have a linear relationship with outcome. And unless we're rigorous in exploring this assumption, we may be either overestimating or underestimating the association. However, it's considered the more useful tool than other approaches, particularly because many people who are trained in research understand the methodologies. As you get to more advanced methodologies, it can be very difficult to explain to your readers what it is that you're doing. But that's no excuse not to use the best statistical method that you can. However, regression techniques have remained fairly common in public health and epidemiological literature. They are becoming more sophisticated as we go into especially big data analysis. We're not going to talk about that today. This is a good foundation. So for multiple linear regression, we have a continuous outcome measure, y, and then our independent variables are denoted by a series of x's, x1, x2, up to any number of variables that we want to include. Now, we can't get too greedy because we are somewhat limited by our sample size. And there are some conventional rules about how many variables you can include in a model. You can actually include more in a linear regression model than you can in a logistic regression model because of the nature of the outcome being linear. You always have more power in a linear regression model than you do logistic regression. That said, we're always striving to get what we call a parsimonious model, or a good representation of the data. And we don't want to include too many extraneous variables that are just there, not really doing anything. But if they do have some effect on outcome, or they do have some sort of confounding effect, it is really important to try to include them. This is one reason why when we're developing a study, we plan for a certain number of covariates or variables. And to do so, we need to have a certain sample size in addition to looking for some sort of mean effect. So that is something to consider. And a rule of thumb, about 20 cases or observations per variable. There are other rules of thumb out there. And again, it depends a little bit on how common the outcome is or how common the exposure is. But those are some general rules of thumb. So if I have a study with 100 people, I might get away with 5 to 6 covariates. If I have 10,000 participants, then I can have 50 variables. The problem there, though, is that you really do need to make sure that each of those variables you're putting in the model is there for a reason and is interpretable, and also isn't accidentally adding too much explanatory power that may be actually too closely related to the outcome of interest. And we see that in one of the examples where we're looking at the outcome of hypertension status and including systolic blood pressure and diastolic blood pressure as predictors of hypertension. Well, it really doesn't make sense to include those two variables because the very definition of hypertension is to have elevated values on systolic or diastolic blood pressure. So including them in a model doesn't really make sense. So we shouldn't just throw things in that are predictive. Economists would argue differently. They tend to throw everything into the model. In health sciences, though, we're really keen on interpretability. And so we do try to strive towards what we call parsimonious models or more simple models. Again, in a multiple logistic regression model, it's very similar to a linear regression model. In fact, when you go into SAS, you'll see that logistic regression is listed under linear models. That's because the outcome y is a linear function of the covariates. The outcome is the log odds of the event of interest. So again, log odds, we don't touch that too much in terms of interpretation, but in terms of the mathematics of it and what's behind this model is this linear association between the variable and the outcome. And so we should be mindful of testing to see if that's an appropriate model in terms of our data before proceeding to a full-blown multiple logistic regression model. Okay, but in terms of thinking about the model with a dependent variable, we have an intercept, which is where the x and y axis would meet, and then the predictors or covariates denoted a beta coefficient and a variable x. Those models are very similar, linear and logistic. The difficulty is with logistic regression coefficients, they're not always easy to interpret. Like I said, it's the log odds. So we have to convert them. Technically, with a logistic regression coefficient, not the odds ratio, but the coefficient, with a dichotomous predictor X, the beta 1 that we obtain is a log odds ratio for success or membership in the outcome group. And so if you go from exposed to not exposed, it's the log odds of being in the outcome group. Doesn't make a whole lot of sense intuitively. However, we can use it to understand the general direction of the relationship. And with a continuous predictor in a logistic regression model, our beta coefficient is the log odds ratio per unit change in X. Again, we're going to want to convert these to odds ratios. So for interpretation, what we do is we take the constant E, which is the base of the natural logarithm. So think of it as like pi. It's a constant variable or constant value. We raise that to the beta power, and that will give us our odds ratio. If you want to run the math on that one and how that is true, that's a different, that's for mathematicians to do. However, by taking the exponent of E, we can get the odds ratio. Don't worry though, you don't have to do it yourself. You can let the statistical software do that, or you can use a calculator to do that. So, ultimately from a logistic regression, we want to obtain odds ratios and adjusted odds ratios. And thankfully our stats programs automatically do that for us. So we can interpret coefficients, raw coefficients from a logistic regression model in a kind of vague kind of way. So a beta coefficient of 0 would indicate no association. And the statistical tests that are performed are actually that your beta is 0. Not surprisingly, our null hypothesis is that for each of the betas is that they are 0. A beta coefficient in a logistic regression greater than 0, it suggests an increased probability of increase in the log odds of the event as X increases. A negative value would indicate that the probability of the event of interest decreases as X increases. But that's about as far as we're going to get as far as understanding what that beta coefficient actually means. But it can tell us the overall direction, which is useful. But when we convert it to an odds ratio, we have to be mindful of how odds ratios work. An odds ratio greater than 1 suggests a risk factor or increased risk or increased odds of the event happening. An odds ratio of 1 equals no association between Y and X. The odds are even, and so even, same value divided by the same value equals 1. And then an odds ratio of less than 1, then we say that it decreases the likelihood of the outcome, and we call that a protective factor. So just be mindful of that as you're going between beta coefficients and odds ratios, that a negative beta coefficient will translate to an odds ratio below 1. A positive beta will result in an odds ratio greater than 1. And then an odds ratio around 1 will be close to 0 as far as the beta coefficient. But like I said, we are going to, more often than not, rely on looking at the odds ratios. So we don't generally interpret the beta coefficients. As an example, here's a multiple logistic regression model of hypertension. And the outcome is yes, you do have hypertension, versus no, 0. Okay, so dichotomous outcome. And here are the results of our model that includes 3 variables: age, male sex, and BMI, body mass index. And do notice that in our output here, we do have the beta coefficients. And we can, like I said, say that a negative value indicates lower likelihood of the outcome or lower probability of the outcome. A positive value equals a greater likelihood of the outcome. And you can see this then in the odds ratio. With the positive value, we have a positive odds ratio above 1, I should say, of 1.05. So basically, each year of age, the odds of hypertension increase roughly 5%. Odds ratios are a little tricky to print. You can think of that as 105% of the risk, which is like saying 5% increased risk. So basically your hypertension risk goes up 5% per year. Lucky us. It's one reason why when we go into the doctor, they always take our blood pressure. It's not just medical theater. Your likelihood of hypertension increases with age ever so slightly. Now you know by how much. And here's a confidence interval around this estimate again. Thank you, SAS, for computing that confidence interval for us. Okay, for male sex, it actually appears to be a protective effect for hypertension. I don't know if that's true or not. That's what our model's telling us. I could come up with all kinds of plausible scenarios of why that might be. One might be that males simply die sooner, and so they're less likely to develop hypertension in the first place. It's a competing risk issue. Or it's biologically true. It's not, that's really not our goal here. But the point is that it has a protective effect. So membership in the category male has a protective effect with respect to hypertension, adjusting for age, adjusting also for BMI. And then finally for BMI, we saw that it was a positive here, but here's what we can actually interpret here in terms of an odds ratio. About a 17% increase in risk as you go one click on BMI, and that's, on average. So one unit increase in BMI, so from going 25 to 26 or 26 to 27 and so on average that increases the risk by around 17% for each level of BMI based on this model. But that's how we would interpret this. And you can see how useful this is because instead of just having a 2x2 table, we can throw in all kinds of adjustment variables and get adjusted odds ratios, okay? Now, as a preliminary step, let's say I was mostly interested in BMI. I could have calculated a crude odds ratio with just BMI in the model and then see to what effect other things affect that relationship. Here, I have just thrown them in the model, and this is what output would look like. But we could start with, if we're interested in one risk factor primarily, get its crude estimate and then adjust accordingly. Okay, it is important to keep in mind when you see the odds ratio in logistic regression output that it's for a 1 unit change in the variable x. And so unlike linear regression, where we can simply multiply the coefficient to say what it would be for a 5 unit change or a 10 unit change, we have to be really careful with odds ratios because we can't just multiply them. So to obtain the odds ratio for a multiple unit change, we must multiply first the beta coefficient and then recalculate the odds ratio. For example, for a 5 unit change, we would take that value E, that constant. It's on your scientific calculator if you're looking for it. I think in Excel it would be EXP would be the what you type in, raised to the beta power times 5 for a 5 unit change. Okay, so if I want to know what 5 years of age meant in terms of hypertension, I couldn't just say 5 times 105. That would give me an odds ratio of 5, which would mean that you have 5 times risk after 5 years. That would be terrible. And so we wouldn't want that. So what we have to do is first multiply the beta coefficient and then calculate the odds ratio. And this is a mathematical issue. And I could demonstrate it to you, but I think you get it, that you have to first deal with the coefficient and then you can get the odds ratio. Likewise, you would have to calculate new confidence intervals around that if that was your goal. Another approach would be to simply divide. You could divide age by 5 in the original data set in terms of 5 units. That may not sound really intuitive, but then each unit becomes 5 years. Think of it this way: if I were to divide it by 10, that would be decades of life, right? So if you're 40 years old divided by 10, you've had 4 decades of life. And so therefore your coefficient would be 4 decades of life instead of years of life. That's one trick that you could do to make it so that your odds ratios are interpretable. And that's why you should always say what your units are. And so I just want to emphasize that caution. You can't just multiply the odds ratio for a multi-unit change in X. We can do that in multiple linear regression. We can simply, once we get our estimates, these are for a 1-unit change in X, and it's in the units of our outcome variable. So here we have, moving to linear regression, you can see that the output is fairly similar. No need to convert it to odds ratios because it's directly interpretable. Our outcome is infant birth weight in grams. So typical normal birth weight, 2,500 grams, plus or minus 500 grams, at birth, some smaller, but let's just say around 2,500 grams would be typical or normal. And so that'll help frame grams because we don't really think in terms of grams that often. Okay, so here we have a model predicting infant birth weight. So in this model, we have male sex, gestational age in weeks, and mother's age in years. So, and that's male sex of the toddler or the infant. What does this mean? Okay, so I'm going to ignore the intercept right now. That is when you set everything to 0. So that would be the theoretical size of 0 age. Mother is 0 years old. So the intercept here is not necessarily interpretable, but we need it to calculate predicted values if we want to calculate predicted values. Okay, so male gender of the newborn, it predicts a 175 gram difference, and that's it. That's all as far as you can go on that variable. Okay, and so that we all know that male babies tend to be a little bit heavier on average, but that's just on average. It's certainly not always true, but that is statistically significant. It's one of those, yeah, duh. Gestational age, 179.9 grams per week is what you would expect. So basically this study had the gestational age. Some are born at 40 weeks, some are 39, some are 32, some are as early as 24. Before that, it's not very likely. But in any case, for each week from basically 24 to, let's say, 42 for a delayed, that would be what you'd expect for each week of gestation in terms of weight, on average, 179 grams. And then mother's age in years, so for each year of age of the mother, 1 gram is the linear estimate here of what happens in terms of birth weight. Not only is it not statistically significant, you can see here, that would be mighty small amount clinically as well, 1 little gram. However, gestational age obviously is a strong predictor of birth weight, which we know, of course, but this is an estimate based on the model that it would be 180 grams per week, which is fairly substantial. So for a 1-year change in mother's age, we predict a 1.3 gram in birth weight. So the clinical significance matches the statistical significance. A 5-year change in mother's age would predict, we simply take that coefficient, 1.35, multiply it by 5, a whopping 6.9 grams, so not a huge difference. And then and it's not statistically significant. It doesn't matter what we multiply by, it's not going to be statistically significant. In fact, it would not change the p-value. That's just so that we can interpret it in terms of other units. Okay, so 6.9 is not much, even for 5 years. However, 1 week of gestational age predicts a weight increase of, let me get my face out of the way, 180 grams. 5 weeks of gestational age would be 900 grams. Okay, so not only is it statistically significant, it's also clinically meaningful. 900 grams would be roughly 30 to 40% of total birth weight. So obviously, gestational age is a huge predictor. And you might be saying, well, yeah, no, but this is one, from a large sample of infants, this is what you predict in terms of gestational age. Okay, so, and the point of showing you that was not one of the predictors of infant birth weight, but how in a multiple linear regression model, the coefficients are directly interpretable in terms of the units of the outcome. And likewise, it's for a 1 unit change in each of those predictors. Logistic regression, it's also for a 1 unit change in the independent variables, but to understand what's happening to the dependent variable, we express that in odds ratios. Okay, and so doing adjusted analysis, there's really no equivalent in linear regression other than doing linear regression. Logistic regression, we kind of have the option of doing the Cochran-Mantel-Haenszel method. Now, the Cochran-Mantel-Haenszel method, which we discussed a little bit previously, is when we use basically 2 by 2 by 2 by 2 by 2 tables, and we just keep cutting it and then get adjusted estimates that way. The limitation there is that we can only include stratifying variables. We can't, and it could be multiple categories. It doesn't have to be 2 by 2. It could be 2 by 2 by 3. But still, it would still be categorical in nature. And so as soon as we wanted to introduce any kind of continuous variable, we would have to move over to logistic regression. So I do recommend, however, if your outcome is dichotomous, to get as far as you can using stratified analysis to first understand what's going on and then move over to logistic regression. And you do lose information if you use purely categorical data, and you also lose power when you make something categorical. And so there's good reasons to use logistic regression. But for exploring effect modification, exploring confounding, it's sometimes easier to see what's happening with 2 by 2 tables, especially if you look at the tables and see what happens in terms of percentages. It's easier for you to get your head around it, I think, than looking at odds ratios. So I just wanted to share a quick example of how similar Mantel-Haenszel adjustment would be to logistic regression if we were simply using categorical variables. And forgive me if the details on the screen are not terribly clear. I'm going to highlight them up for you. So I'm basically doing the same thing using 2 by 2 by 2 tables and logistic regression. And my outcome is imaging. This is my little pet project. Imaging, and I am looking at the association between having any chronic disease, so cardiovascular disease, asthma, anything, if that predicts whether someone gets imaging or not, okay? And so what I have here, this is the 2 by 2 approach. And I find that those who have a chronic disease, a 1, 79% got imaging. For those who didn't have a chronic disease, 66% got imaging. So a 13% difference in the proportion who received imaging. Not small. The p-value associated with this chi-square test is p equals 0.01. So it is statistically significant, our cutoff being 0.05. Okay, so this is a fairly modest association between having a chronic disease present and the use of imaging. I'll make an argument that if somebody already has a disease, you might be less likely to, or you might be more likely to use an image just to see what else is going on. While you're in there, you may as well see what else is going on. I'm making up a reason. But we do have this association, okay? However, if I stratify the result, and this is, we're going to move down here. So what I did is I took that 2x2 table and then I added a stratifying variable, which you can do in SAS. And I simply cut it at above 21 and below 21 in terms of age. Because again, I can't use a continuous measure. I'm just going to use a cutoff of age. If I adjust for age, my adjusted odds ratio comes out to 1.18. Okay, so my crude estimate was 1.93. Sorry if I didn't say it before. The odds ratio was 1.93, the crude estimate. Statistically significant confidence interval 1.16 to 3.22. Here I am ready to write my paper about how chronic disease predicts use of imaging after concussion. The most interesting paper ever. And then I get my stratified results by age, and it all but disappears. The odds ratio is 1.18, 95% confidence interval is 0.68 to 2.06. It overlaps 1. I didn't get the p-value out of there, but it's not statistically significant. So that's an example of confounding. Age is a confounding factor here. And we knew, could have thought this. We already know that age is associated with imaging from previous bivariate analysis. It makes sense that having chronic conditions would also be associated with age. And so it ends up that age is a confounder. But what I want to focus our attention on here is that my estimate from the 2x2 table, odds ratio 1.93, confidence interval 1.16, 3.22, p-value 0.01. Okay, and then our Mantel-Haenszel adjusted 1.18. Okay, over here I'm doing a logistic regression model. So I've set up my outcome as yes, no, any imaging. I've thrown in the variable first, just chronic disease, to get my crude estimate of the odds ratio. By crude, it just means using a simple logistic regression, chronic disease against outcome. And lo and behold, here's my point estimate, beta 0.6617. Don't forget, the betas are hard to interpret. The odds ratio estimate, which it automatically generated for me, thank you, SAS, 1.938, the exact same value as we got over here using a 2x2 table. And in fact, my confidence intervals are also the same, 1.163, 3.23. This one's looks a little different just because of the rounding. How do you get the exact same answer? Why don't I just use the 2x2 table? It gives me the right answer. Well, the answer is there is no good reason for a simple logistic regression. It's going to have the exact same result. And in this case, since all I did was stratify by another categorical variable, my adjusted estimate down here, this is part of the logistic, 1.183. 1.183, they're the same. Confidence interval 0.677 to 0.069. Okay, so I end up with the same result. That's good because we would want to get the same answer because there's supposed to be useful tools. The difference is that if I were to continue to stratify, first of all, I can't include continuous measures. And I also might start to get really sparse cell counts in here. Logistic regression is going to handle that a lot better as I start to get sparser cell counts, although that's still an issue in logistic regression. But I can include things like age as a continuous variable. I don't have to dichotomize it as above 21, less than 21. So that's the difference, is that maybe I could do a more refined adjustment by age, or I can include more variables by using logistic regression. But again, the 2x2 table approach for logistic regression or for dichotomous outcomes is a really nice complementary tool or substitute. And sometimes it's easier to interpret a 2x2 table because you also have percentages and things like that. So do with that what you will. But there is this kind of emphasis on using models all the time where I argue that Mantel-Haenszel could be just as good in many cases. So I would suggest using the stratified approach to identify confounders, effect modifiers, strength of association before turning to more complex models. There are parallel things you could do for linear regression. You could do partial correlations and things like that. often it's easier just to move straight on to the linear regression model, to be perfectly honest. Because the fact that odds ratios are such a goofy thing as far as interpretation. So in statistical analysis, we start from univariate descriptive analysis, build towards bivariate analysis, and then finally towards multivariate and inferential statistics. And so all of the tools that we've learned along the way, it's not like we throw those things away and we move straight to multivariate analysis. All of them inform each other. And we should start from the basic and work our way up to the more complex. That also helps us get our heads around what's happening. It also, if we're presenting it in a manuscript, helps the reader to understand, okay, well, what was the crude association? What was the adjusted association? What are some of the subgroup differences that we might see? If you take your reader through your analysis path, it also helps them to understand what's happening. If you just present a table from multiple regression, it's very hard to get your head around it. And so I suggest doing it both for yourself and for your reader. So it's important not to skip any steps and rush to multivariate analysis. You should know your data well before putting it into a multivariate model. That doesn't mean performing lots and lots of small statistical tests necessarily, because you can get yourself in trouble there when you're making too many comparisons. Your likelihood of making type 1 error increases as you do lots of tests. But just kind of getting your head around what's associated with what before you throw it into a multivariate model. And that's another reason why we specify in advance what is the ultimate test that we're going to use to determine the relationship with this variable. And usually we'll say, okay, we're going to present our adjusted results. It's our main test. You will see papers with tons of p-values in them, and we all do it. But ultimately, there should be a limited number of formal statistical tests presented. All of your work in biostatistics should be guided by an analysis plan and the methodology. It's all about finding the right tool to fit the research question, to fit the level of measurement, to fit the assumptions that we have for these different distributions, if it's just distributional assumptions apply. And so it's just a matter of picking the right tool for the job. We don't try to use 6 different approaches just to do 6 different approaches. But you can kind of start to see how these things build on each other. The most obvious example would be the stratified analysis working its way towards logistic regression. But there's other ways in which there's a lot of similarities between, let's say, linear regression and ANOVA, which we're not going to really get into. But there are kind of logical and natural progressions between these different statistical steps. So that's it for today. The final lecture will be on survival analysis. And the main reason why I wanted to present survival analysis is that a lot of the medical literature and epidemiological literature will present survival analysis, partially because of the nature of study designs where we have to kind of cut it off at some point. We can't follow people forever. So in clinical trials after 2 years or a longitudinal cohort of a couple of years, we cut off the data artificially. And so survival analysis allows us to look at not only outcome, but time to event, and it's super powerful. And so I at least wanted to introduce it more from a statistical literacy standpoint than something that you might apply. If you wanted to further your statistical training, I highly recommend taking courses separately on survival analysis, especially if you wanted to get working on a clinical trial or doing that kind of investigation. There are also opportunities to take courses specifically in logistic regression or linear regression. There's other advanced techniques that you can learn, but we've gotten pretty far by getting through multivariate regression.